So in this one, I want to return to the subject of autonomous equations. Recall that autonomous equations are first order, or for us, they're going to be first order differential equations, uh, for which the derivative of the dependent variable depends only on the dependent variable. There is no in particular dependence on the independent variable. So if the independent variable, for example, is time, as it very often is, then what we're saying with an autonomous equation is that this is something that doesn't depend on time. And we've looked at many examples of autonomous equations in the past. We looked at, for example, the exponential growth, the exponential decay equation, radioactive decay. These phenomena are time independent, all right? So it doesn't matter. All that matters about these, and we'll elaborate on this a little bit, all that matters in terms of describing the state of such a system is the value of the dependent variable. Nothing else matters. Another example of a time independent system would be something like Newton's law of cooling, right? It doesn't matter when you put the cup of coffee, at what time you put the cup of coffee in the ambient, in the room temperature room. It will cool in exactly the same way. You can do that at 10 a.m. or 11 a.m. and it doesn't matter, right? So that's an example of an autonomous system. And the differential equation should reflect that. The differential equation which models that phenomenon. Just some note on notation before we keep going here about autonomous equations. So in this section and in many future sections, we're going to do the following strange move. We're going to start thinking of x as being our dependent variable. Okay, x is going to be dependent on the independent variable t. We're going to do this for reasons because later on when we talk about systems of differential equations, we're going to have multiple dependent variables like an x and a y, and we want both of those to be dependent on an independent variable, which we're going to think of as which we're going to call t, but we're going to think of in the back of our mind as being time. And the reason why we choose the letter t is because t is the first letter of the word time. Okay, so an autonomous equation here, and just maybe I'll make that warning more explicit. So warning, x is the dependent variable on t in this section. I'll say in this discussion. Okay, and it will be the case that it's going to be the dependent variable often. I mean, we're not used to this because we usually think of x as being an independent variable, and other stuff like y depends on x in some way, right? We do this this is often the convention that is used in, say, calculus classes. But here, this is a little bit different, okay? And I just wanted to point that out to you. Okay, so what is an autonomous equation? So an autonomous equation in this setup would look like dx dt, which is a synonym for x prime, equaling some function of x only. Okay? Now, again, we've talked about these, and actually we've talked in particular about how to solve these explicitly, find the general solution, all that. Because notice that this is what's called a separable equation. This is separable. You can separate the x terms from the t terms. You can put on either side of the equal sign. The equal sign becomes like the Berlin Wall, right? And so once you do that, you integrate both sides and then you win. Remember, this is this whole separability idea. And that's all well and good, but sometimes we don't want to, or sometimes we don't need to go into all of that detail to find the information from the differential equation that we really care about. So I want to have a more extended discussion about autonomous equations here and now. First, one fact that I want you to recall is about their slope fields. So don't forget slope fields of autonomous equations. Are what are called horizontally invariant. And now what does that mean? That means that you can take the slope field of an autonomous equation and just shift it any amount in the horizontal direction, and it won't change. Okay, it's horizontally invariant. You can move it around like this. Let me show you an example of the slope field of an autonomous equation from the textbook. I think I've got it here. Oh, sorry. Where is it? Here's one. So this was from the section in on slope fields, and you can see here in figure 1.5. Look at this slope field. Can I copy this? Copy image. Maybe I'll move it to my page. Paste. Allow paste. Okay, there we go. Cool. And here is a slope field, which of an autonomous equation. In this case, this is y prime equals y. So this indeed does follow this format of this form of an autonomous equation. And you can see, I hope, forget about the red lines. Those are the integral curves. Forget about those. Look at the slope field itself, the little blue line segments. And notice that if I were to move the slope field, if I was to lift it up and move it horizontally and put it back down again, it would be the same slope field. That's what we mean. It doesn't change. It's invariant under horizontal translations. That's what I mean by horizontal invariant. Okay? Another feature to notice about this slope field are the integral curves. You see that these integral curves, it seems like all of these three integral curves that are pictured here, they all seem to be converging as the independent variable gets larger and larger. They all seem to be converging on a particular solution. And there is one solution here which is not drawn, but which is clear. So remember, this is y prime equals y. There's one solution here which is hopefully very clear. This is, oh, and actually, let me write it a different way. This is actually x prime equals x in our new notation. Yeah. So what is playing the role of f of x is x. There's a solution which is namely x equal to 0. Or excuse me, yes, x equal to 0. Because remember, x is now tracked on the vertical direction. I'm used to thinking of x equal to 0 as being a vertical line, namely the y-axis. But no, this is the t-axis now, and this is the x-axis. Okay, you're gonna have to deal with that change in thinking. Okay. But what I'm trying to point out here is that x equal to 0 is a solution. And what I want you to observe is that it feels like the other solutions converge on that solution. All right? We can sort of generalize this observation. Let me maybe just show you another example here. Let me grab another one from the textbook. I know that here in the section on autonomous equations, good, we have this one here. Let me copy this image and paste it over. Maybe I'll put it down here. Paste. Allow paste. Why doesn't it just let me do that all the time? Here's another one. Again, notice, just ignore the red lines. I know they're complicated looking, but look at the blue lines. Look at the blue slope field. And notice that it's horizontally invariant. This is an autonomous equation, okay? And here we see these two lines here. Oh, shoot. Maybe I'll draw them in purple. Here's one of them. It's horizontal, completely horizontal, and this one here. These are solutions to the differential equation, okay? There's two of them in this case, whereas in this picture there was one horizontal solution, constant solution, okay? Can we figure out what's going on with these solutions? And maybe I should write the equation of this. What was it again? I forgot. It's 0.1x times 5 minus x. So this one was x prime is equal to 0.1x times 5 minus x. And maybe you can observe something. Where are these purple solutions? These horizontal line solutions, they correspond to places where this right-hand side are 0, right? It's 0 when x is 5, and it's 0 when x is 0. And indeed, that's the two solutions that we get here and here, yeah? Okay, so let's characterize what's going on there. So we make the following definition. We call x equal to c a critical value if f of c is equal to 0. So in the context of autonomous equations, we're going to call x equal to c a critical value if f of c is equal to 0. And the thing that I want you to observe is that x equal to c is a solution to dx dt equals f of x. Is this clear? Because think about it, right? So if we plug in, if we take x equal to c to be, we think of that as a constant function, okay? If we plug in that c into the right-hand side here, we get 0. Doi, right? That's clear because f of c is 0 by definition of being a critical point, yeah? A critical value. On the other hand, what is dx dt if x is equal to c? If x is a constant, then dx dt is 0 no matter what. So indeed, for this choice of x, this equation checks out. Dx dt is 0 because it's a constant function, and f of x is equal to 0 because it's a critical value. Okay? That's exactly what's going on with these purple horizontal solutions. This one here is exactly a solution to f of x being equal to 0. In particular, f of 0 is 0, where f of x is x. And similarly down here, the two values of x which make this side here equal to 0 are 0 and 5. And you see 0 and 5 are the horizontal constant solutions, okay? Now, we're also going to we call these solutions here equilibria solutions. These constant function solutions equilibrium solutions. Okay? Just think of it as terminology, yeah? And they're very easy to detect, okay? The process of detecting an equilibrium solution or finding the equilibria solutions is simply to take this f of x here and set it equal to 0 and solve. That's all you have to do. So for example, if you have x prime equaling x squared minus 6x plus 8, there is an autonomous equation, okay? The equilibrium solution, so equilibrium solutions, are found by solving the equation x squared minus 6x plus 8 equals 0. In other words, finding the critical values. Oh, is this doable? Maybe I messed up. Oh, no, I didn't. Wait, I don't know. I can't tell. I'm not very good at math. This is x minus 4 times x minus 2, I think. God, I don't know. That's right. Look, I did it. Okay, good. And so in particular, x equal to 4 and 2, or 2 and 4 are our critical values, and hence x equal to 2 and 4 are equilibrium solutions. Do you believe it? Because just plug in x equal to 2, for example, back into the original differential equation. Plug in x equal to 2 into here. What's x prime? That's 0. And what is x squared minus 6x plus 8? Also 0. And so therefore, and we know 0 is equal to 0 in this universe, and therefore x equal to 2 is a solution. Similarly, x equal to 4 is a solution. Okay? I won't belabor this point, but this is how you find equilibrium solutions. Okay? Good. And I'll just sort of leave it there for now. We'll talk about some more concepts in the next one, but this is enough for now. Bye. See you in the next one.